Okay, welcome everybody to this new DaSCI seminar. Today's speaker is Ziyu Yao, Assistant Professor in the Department of Computer Science at George Mason University, where she co-leads the George Mason NLP group. She works on LLM reasoning, planning, mechanistic interpretability, and human LLM interaction. Prior to George Mason, she got her PhD in computer science and engineering from The Ohio State University in 2021. And today's talk will be focused on mechanistically interpreting language models from syntactic code completion to arithmetic reasoning. I want to thank again Professor Yao for very kindly accepting our invitation. And whenever you are ready, the floor is all yours.
Yeah, thank you very much. And thanks for this very nice introduction and invitation. So yeah, I'm very happy today to introduce some of the recent research in my group. I think everyone here is already very familiar with like language models. And if you think about how these days people are evaluating language models or how we get to know more about a language model, certainly you'll think about a lot of different benchmarks. So for example, like whenever a big company releases a new language model, you'll see that they will publish the results of this language model on a tons of different benchmark data sets, and they will also compare their model's performance with the performance of other older language models. So those benchmark data sets have shown us a lot of empirical insights about what those language models are good at or bad at. But the problem is with those results, we still don't understand, for example, when those language models succeed, do they actually succeed for the right reason? And similarly, if we see, say, a language model achieves like a low performance on a certain benchmark data sets, we want to understand like why those language models could fail on this task and what happens under the hood. So only those benchmark data sets or the empirical results that we can observe from running the evaluating the output from the language model does not tell us anything about their internal mechanism. And this is a big problem because today we talk about AI safety. We talk about how humans should establish proper trust in AI models. If we know nothing about internally what happens to those language models, very, very difficult for us to have a proper understanding and assessments on the potential risks and benefits of those language models. Motivated by that, in the recent years, my students and I have been working on a topic called mechanistic interpretability of language models. Just to give people some background, so you might have heard about more classic interpretability approaches like line sharply value. So those can be considered as the behavioral interpretability, where we do not attempt to like open the black box of this model. And instead, what we typically do is to perturb the inputs to this model. And then we'll observe how the model's output will change after our perturbation. And by observing the reactions of a certain model's output to the changes of its inputs, we can somehow get a sense about how this model could like consider different input features being important or less important, and how we can like utilize this information to somehow get a sense about where this model can do well or do bad. But the problem is only looking at the external behavior does not give us too much insight about, say, how could we further improve this model. So mechanistic interpretability is getting very popular recently. And in contrast to the behavioral interpretability, in mechanistic interpretability, we really try to open the black box and look into the internal of a certain model. And in case of language models, for example, what we really want to do with mechanistic interpretability is to understand internally how those language models function to implement a specific behavior or capability. And this intuitively will bring us more insights than just looking at the external behavior of the language model. I know today we have like many PhD students, so I also prepare a few pages just as a background information about this field. But generally speaking, MechInterp mainly study three things. The first thing is we want to understand what kind of features have been encoded in the representation of a model. So for example, if you input a sentence containing a certain token, say dog, right? Then you might want to check whether the representation of this token internally in the language model has encoded different kinds of information about dog. Say it's an animal, it's a pet, it has like 4 legs, and so on and so forth. And building on top, in MI, we also study circuits. So circuits is the computational pathways, how a model internally connects and utilize different features such that it can eventually implement a specific behavior. So to give you a very quick example, let's consider how a language model could generate tokens to complete a person's name, which is very helpful, say in a long context, say a story generation scenario. An example we saw here is to generate the person Dursley's name, which is a character from Harry Potter. So an early research discovered these circuits, and we find that this circuit has 2 major attention heads. And the first attention head is the previous token head. And this is a head that attends to the previous token to the current position. And by doing that, this head further writes into the representation of the current token. And the representation basically says that, okay, the URS token follows the D token, right? And then this information is further utilized by the induction head, which will try to induce, say, now if I'm receiving the input letter D here, then what should be the next word to be generated here, the next token, right? So in this case, because we know that URS follows the D token, so as a result, when we see the letter D, we'll know that, okay, the URS token should be the next token, so that this language model can generate a complete human name without mistake. So this is like a very, very straightforward, very simple example of circuits that people in the MechInterp community has been pursuing. But it is actually not an easy task to discover such a circuits. And in my talk today, I will also talk about how we try to mitigate the heavy labor or the problems that people have encountered when they are trying to discover circuits in order to understand the language model. And finally, MechInterp also include the study of universality, which means that, say, for those features and the circuits that we discovered from one language model from one specific task, do they also generalize across different language models and different tasks? So this can be very helpful because, for example, if you think about like scaling law of language models, and you think about the difficulty of interpreting a very large language models, then you see that, say, if the insight that we discover from a relatively smaller size of language model can generalize to the larger size of language model, then this can be super helpful, and you will save us a lot of effort in repetitively interpreting more and more language models on different tasks. So overall, this is the 3 key objects in the MI study. So if you are interested in this topic, we recently have a very comprehensive survey on this topic. And we also just presented a tutorial on the topic at ICML this year. So we have all the slides and video available online for people who are interested in it. Okay, so along this line, in my talk today, I want to present to you 2 recent projects in my group. In the first project, we'll focus more on understanding how language model could fail in some like even very straightforward task. And the specific task we'll focus on is called syntactic code completion. And we'll hope to see how by doing this mechanistic interpretability, we'll be able to understand the reason and also further improve the model. And then in the second project, I will talk more about, say, when a language model succeeds, is there a way for us to mechanistically understand how it succeeds? And more specifically, we hope to understand whether a language model succeeds for the right reason so that we can have a good assessment on, say, would this success actually bring any potential risk? Okay, so we'll get started with the first one. So this is a project, a paper that is recently accepted to new RIPS this year in collaboration with my students and also a professor in University of Central Florida. So in this project, we study how language model generate code. Code generation has been a very popular task in recent years. And it's not only because it is so useful in practice, it is also that because that like code generation can be a very good test bed. Like a code snippet has both like syntax and semantic. It has a lot of structure representation, so it allows us to test a lot of things. And in recent years, you might have heard about different code language models like Codex, CodeGen, DeepSeek Coder, and also a lot of language model agents specifically defined to support software engineering tasks. And this is actually also the topic that I have been working on since I was a PhD study. So for all kinds of reasons, we picked this task and we want to see how language model can actually do in whether the language model will do well in this task. So surprisingly, a recent study discovered that even state-of-the-art language models could still fail in a very straightforward syntactic code completion problem. So this is like a statistic from this recent paper where the authors tested several recent like billion parameter scales of language models. And they find that even for those language models, there's still a certain percentage of mistakes generated by those models coming from incomplete syntax structure. And one particular example is about how those language models fail to close the parentheses in a balanced way. Say on the left, you actually have like 4 open parentheses. So then on the right, to close it, you should generate 4 right parentheses. But even for this like very, very straightforward syntactic code completion problem, language models still make mistake. So we are very curious about like why this could happen. So in order to more systematically understand this phenomenon, we created a synthetic data set to more carefully understand the current limitation of language model on such tasks. And the specific 4 subtasks that we created all follow like roughly the same format. And basically, it starts with the input to the language model start with the dot string comment, saying that you are going to print a certain number as the string. And then we also give like the prints optionally with a few string functions and followed by the specific number that we want a language model to like print. And the task for the language model is to generate the correct number of closing parentheses so that eventually we have like balanced parentheses in the complete code statement. So totally we have like first task, which demands only 1 closing parentheses. Second task demands 2, third one demands 3, and the last one demands 4. So one interesting detail I'd like to mention here is that the way how language models generate the parentheses is actually very different from how humans will do that. Here, I'm showing the tokenization results of, I believe that's a Llama 3 yeah, I think that's a Llama 3 language model. So you can see that for humans, we typically like write the closing parentheses 1 by 1, but actually from the language model's perspective, they typically generate multiple parentheses together as just 1 single token. So for example, like these double closing parentheses together, it is one specific token. And then actually, if you have like up to like 4 different closing parentheses, they will still be represented as just one independent token to be generated by the language model. But say if you have here, you have like 5 closing parentheses to generate, language model will actually break it down into 2 plus 3. So yeah, so this is actually very, very different from like how humans understand or write down the closing parentheses. So in our task, we only consider up to 4 closing parentheses as the expected token. This is just to simplify our settings so that eventually when we analyze the model, we only care about, say, for the next token, does the language model generate the correct number of closing parentheses in a single token? And we don't have to worry about like sequential token generation. Now, let me just show you a few results. So we tested different language models of different sizes, including some billion parameter levels language models on this task. And we see that for all of those models, they can succeed in the 1-paren and the 2-paren subtasks without problem. And for the 7 billion scale language models, they also do very well in the 3-paren case. But then we see that in the 4-paren subtask, all of those smaller GPT-2 models, they fail to do this task successfully. And surprisingly, even for the 7 billion Llama 2 model, it has almost just 0% accuracy on this 4-paren subtask. So for CoLlama and Pythia, they have like much better results, but still there's like 10% or 20% performance gap. And note again that this is such a straightforward task that even the entry level or like programming beginner can easily navigate, but still like language models surprisingly fail in this task. So we started to wonder like why for such a very straightforward syntactic code completion problem, the language model will still fail. Let me first show you the key findings from our project. So the very first key takeaway message from this project says that language models actually do not rely on just a single mechanism in completing this syntactic code, but instead it relies on an ensemble of mechanisms with different levels of reliability to make this prediction. And the second key message from our project is that when we see that language models fail, we may think that maybe it's because the language models do not have the sound mechanisms or very accurate mechanisms in solving the task. But the reality is that language models actually have established very sound mechanisms. But in the meantime, there are also faulty mechanisms developed inside the language model. And it is often that we have too many faulty mechanisms inside the language model, which introduce noise and overshadow the sound mechanisms. So together, in an aggregated effect, we observed that the language model couldn't do well in such a very straightforward task. In the next few pages, I will just further break down how we obtain these 2 key takeaway messages. So first of all, how do we define a mechanism? So actually, we see that in order to understand like what mechanisms a language model has developed, we first will have to somehow decompose this language model. And we are able to do that because of the residual stream formulation of the transformer-based language model. So more specifically, the residual stream is the one shown here. And basically, it says that we can understand how language model gradually updates its representations by letting the multi-head attention and the feed-forward layer to addictively write into the representation. And mathematically, it means that the representation of a language model at layer L is actually the summation of the representation from the previous layer plus the contribution from this multi-head attention and then the representation from the feed-forward layer. And this can be further breakdown into, for example, we can consider this multi-head representation as a aggregated effect from multiple attention heads. And similarly, the representation contribution coming from the feed-forward neural network could also be broken down into the contribution, the additive contributions from the specific feed-forward neurons. So just a little math here, but basically we can decompose the feed-forward representation into a summation of the weighted effects of its individual neurons. And this weighted effects is controlled by a coefficient, which will depend on the specific inputs of your language model. So together, we can see that basically a language model develops its representation by accepting the additive contribution from individual attention heads and also individual feed-forward neurons. So this formulation allows us to have like a top-down and a decomposed perspective in understanding language model. And more specifically, we consider that a language model's final prediction is an additive effect of the predictions made by the individual language model components, such as those attention heads and the feed-forward neurons. And we talk about those components only in the last token position, because that's the position when those components will have direct contribution into the representation, and the representation will eventually be used to predict the next token. And we also consider that every language model component in this last token position represent a certain mechanism. We may not really understand like what particular mechanism it has implemented, but we can imagine this LN component as the tailing or the ending components of the entire mechanism represented or implemented by these components. And we intentionally do that because, as I shown in the very beginning, even for the very straightforward task like completing a human's name, the circuits developed by a language model has been so complicated. So if we want to reverse engineer the exact mechanism of like implemented by every language model components, that would be like a lot of work. So instead of that, we try to abstract away from the need to perform any circuit study. And instead, we only focus on the performance ending by the each individual language model components in the last token position. So in the remaining slides, when I talk about mechanisms, I basically just refer to the language model components or the mechanism represented by those components in the last token position. Okay. Now that we have a way to break down, to decompose the language model into different mechanisms, we first look into like how good those decomposed mechanisms are. And the way we do this can be actually very straightforward. And more specifically, we simply can evaluate the task accuracy of each language model components in the last token position. That means we'll directly use a representation from each component and project it to the vocabulary space. And we see whether the projected vocabulary will have the correct parenthesis token being ranked at top. And here are the histograms, the accuracy histograms of different attention heads for the GPT-2 XL model and the CoLAMA 7 billion model. So for example, here, this is a plot for the 1 paren subtask, and we see that the GPT-2 model actually have like 7 different attention heads that can achieve like 1.0 accuracy on this 1 paren subtask, and similarly for others. So interesting, what we saw here is that for all of the language models, they have developed like different kinds of attention heads with like different kinds of task accuracies. And more interestingly, if you still remember for the GPT-2 XL model, it has like 0% task accuracy on the 3-paren and the 4-paren subtasks. But still, internally, we see that it has developed some like accurate, very sound mechanisms to do this task. So this is something we found to be very surprising because based on our intuition, we may think that, okay, if the model has 0 accuracy on a certain task, maybe it's not possible for the model to have actually developed any useful mechanism to solve the task. But what we observe is completely contrary to our intuition. So we also look at whether there will be mechanisms or components that can generalize across different subtasks. And here we say that if one component can achieve, say, larger than 0.7 task accuracy on multiple subtasks, then we consider these components has implemented a generalized mechanism. So here we show the results from by looking at different attention heads in those models, and we see that there are indeed many heads that can generalize beyond just one single task. They can do well on both tasks. They have high accuracy on both of them, and most surprisingly, we see that okay, first of all, for the Llama model, it actually has a single attention head that achieve almost perfect accuracy on all of the 4 subtasks in our synthetic data set. And this accuracy is even higher than the task accuracy of the Llama model, which is around like 87%. And even more surprisingly, we also noticed that for the GPT-2 XL model, although it has 0 accuracy on the 3-paren and the 4-paren subtasks, internally, it actually has developed a very, very generalized attention head that can work well on across like 3 different subtasks. So again, this is saying that like even though empirically we don't see the language models do well on a certain task, internally it might have already developed like very good mechanisms to solve the tasks. But the problem is that we need to identify those mechanisms. And here are just the attention visualization results for the 2 generalized heads and also one non-generalized head for the comparison. And we can see that for the more generalized heads, they generally have like a very clear attention pattern. Like every time you just attend to the latest like the inner the innerst like function before it's going to complete the code, or maybe the innerst like open parentheses, so that it knows that this is open parentheses that that has not been closed yet. But for the non-generalized heads, we don't see any clear attention pattern. We similarly also look at the generalization of the the feed-forward neurons. And surprisingly, we see that FF neurons cannot generalize to more than 2 subtasks, right? So then it's very interesting, like why could this happen? So we then further conducted some experiments to understand like why FF neurons couldn't do well on like more than 2 tasks. And we follow the typical way how people understand of FF neuron. So more specifically, we'll apply the approach called legit lens. And the idea is that we are going to multiply the each neuron's representation with the unembedding matrix that is typically applied at the output layer for predicting the next token. And by doing this projection, we can directly obtain a logit distribution. And the distribution here is just for the example, but basically what you will obtain is like a distribution with different logit scores for each word in each token in your vocabulary. And also remember that those neurons, FF neurons, they are aggregated by with the weighted coefficients, and these coefficients is dependent on the inputs. And the prior work has tried to understand the semantic meaning of the neurons or the coefficients by saying that, okay, if we have a very positive coefficient, then it's like for the certain neuron, then it's like we are trying to promote top tokens projected from this neuron's representation. And if you have like a relatively smaller coefficient, then that means the language model doesn't want to promote the top tokens projected from the corresponding FF neuron. However, in our study, we noticed that the coefficient can actually be negative as well. And in that case, instead of promoting the top tokens ranked by the logit values, the language model is actually promoting the bottom tokens. So this gives us like a very interesting like binary effects of these coefficients. And it's basically saying that based on these neuron representation, you want to look at not only the top tokens ranked by the logits, but also those bottom tokens, because whether you will eventually promote the top tokens or the bottom tokens will really depend on whether you have a positive or a negative coefficients calculated based on the inputs. So with such an analysis, we eventually discovered that this like binary architecture of the FF neuron has resulted in its limited generalization. So for example, what we've shown here is a logit distribution and the average coefficient for one particular FF neuron in the Llama 3 model. And when we saw that, for example, when the inputs demands one closing parenthesis, initially the one closing parenthesis is not ranked at top by the logit projection, but the language model eventually calculate a negative coefficient such that the bottom tokens will actually be promoted, and that's how the one single closing parenthesis can be promoted eventually. While for other inputs, when we demand the model to generate 2 or 3 or 4 closing parentheses, we see that the coefficients are generally, on average, are all positive. And in that case, the language model is promoting the positive, like the top tokens projected by this neuron's representation. And because of that, because of this like binary coefficient activation pattern, we see that the FF neurons cannot really generalize beyond 2 tasks, right? Because you can either promote one thing or you promote like only the top token or you promote the bottom token. So you cannot promote more than that. And it's like your neuron can only do some kind of like binary classification thing, right? And that's the reason like why we don't see the neuron to generalize beyond just 2 subtasks. And in addition, we also noticed that the model always promotes the 2, 3, and 4 closing parentheses altogether. So that's something we call a noisy promotion. And it says that the language model actually knows that it should pick one token from these 3 choices. But because of the architectural constraints in its design, it's not able to promote only one of them. And instead, what it has to do is to jointly promote all of the 3 tokens. So this introduces the noise in the FF neurons prediction. We have further analysis to look into this noisy promotion, but just as a quick summary, what we notice is that actually this noisy promotion is something indeed existing inside the language model. For example, when we try to understand the precision and the recall of individual components promotion effects, we see that in most cases, we get like from low to high recall of components, but their accuracy is generally like very, very low, and we don't really see any components that with the very, very high precision, like higher than like 0.6 or maybe slightly larger than 0.6, but we don't see like more accurate like promotion effects by any components. And this is saying that when linked models make predictions, what they aggregate are a set of components with like noisy promotions and also low accuracy or low selectivity. So all of those results have then inspired us to make this hypothesis. So we think that the errors in the task of disbalanced parentheses or syntactic code completion do not stem from the absence of sound mechanisms, because we do see like very accurate mechanisms and also like very generalized mechanisms. But rather it is that the influence of the sound mechanisms are overshadowed by the faulty mechanisms. So having this observation, we further propose an approach called RAS-steer. So it stands for like ranking and then steering for the linked model components. And the algorithm works in a very straightforward way. So first, we just rank the linked model components in the last token position based on their generalizability and their promotion effects. So those are the analysis we have just looked at. And then we steer the top ranked linked model components by scaling up its activation by a certain scalar amount. So this is amount like larger than 1.0, so that we can amplify the impact from the sound mechanisms. And together, we see that this simple algorithm can actually improve the model's performance. And those are the results. So so the first row is for the 3-parent subtask. Second row is for the 4-parent subtask. And then first column is when we do the RAS steering, the steering on only the attention heads. And the second column is that when we rank the feed for neurons and steer only those neurons. So we generally see that steering the attention heads is more effective than steering the FF neurons, which is within our expectation, considering that FF neurons have the binary architectural constraints. And another interesting thing we see is that we actually do not really need to steer a lot of attention heads inside a linked model. And typically steering only the top 5 or to top 10 attention heads is completely sufficient for us to improve the model's accuracy from 0% to 100% accuracy. But meanwhile, we also know that on the more challenging 4-parent subtask, this steering will be more challenging. And for example, for the GPT-2 large model, we do have to steer like more heads, and then for the GPT-2 small model, we don't really see this approach to work well. So it might be because this model is just way too small, and the mechanism that we found inside this model is still not good enough for us to improve this model. We also have a comparison with the circuit baseline. So the circuit baseline means that we perform the traditional circuit analysis, like we discover the circuits, and then we steer the attention heads that are considered to be critical in the circuits of this linked model. And interestingly, we see that steering the critical attention heads inside the circuits does not really guarantee a good steering results. And sometimes we also see that, say, after a certain point, if you keep steering more heads included in these circuits, you actually bring some negative impact to the accuracy of the model. So it's very likely that like this circuit introduce some, like the components have some like noise there as well. So what we think be happening is that when we do the steering, it might be more helpful if we directly steer the critical components in the last token position. So those are the components discovered by our approach. And we probably do not want to steer components in the intermediate position of the circuit, because those components do not directly contribute to the final prediction of the model. Yeah, so concerning the time, I'll also like skip a few details here, but basically here, we try to understand, okay, are there any overlap between the critical attention heads discovered by our approach and discovered by the circuit baseline? And we actually see like very different overlap patterns, but we do see that for some models, if we only steer the subset of the shared heads across these two approaches, we can already achieve a high accuracy. And it's basically saying that the language model has developed some redundant mechanisms, and we do not really need to discover all of them. But also for like the relatively smaller size of the language models, we see that their steering effects can be very unstable, and it can be easily disturbed if you steer some components that do not directly contribute to the correct answer prediction. Okay, so yeah, as a quick summary about this part, we bring in this new top-down and decomposed perspective to understand language model, and we see that language models make prediction by not just one single mechanism, but some are bad, and the bad one, the good one are often like overshadowed by the bad one, and that's why we don't see the model succeed in like a very straightforward task. But in the future, there are still a lot more to explore. Like, can we have a more systematic framework to understand these decomposed effects? And other than the promotion, can we also think about how those components can suppress the prediction of a certain token answer? And how do we understand the individual mechanisms developed by each, represented by each components? And how do they happen during the model's training? And finally, we'll hope to study this framework beyond just straightforward syntactic code completion. Yeah, I think I'm a little over the time. I don't know, should I move on or should I pause here for a quick question?
Well, we can do as you want. We will have, I will say, 5 or 10 more minutes to end the talk, and then we could have the Q&A. So we can do
Okay.
as you want.
Okay, then yeah, I can move on then.
Okay, perfect.
Okay. Yeah, so for the second part, I'll just do it quickly, and the takeaway there is also very clear. So again, in the second project, we study like when language models succeed in arithmetic task, like how do they succeed? So this is our paper recently accepted to EMLP. But yeah, I do want everyone to spend 1 second to think about the question, like how do you calculate this arithmetic expression? Okay, so I believe for most people, you will do the first addition first, right? And then you deduct the result by 15, right? So this is actually the very like compositional way how humans will do this arithmetic calculation. It's very elegant, it's very generalizable in the sense that, say, if I have more operations, what you will do is just to keep applying new operations to the previous result, right? And this will also make the calculation very robust. So for the recent language models, we have seen that those language models generally have like a pretty good accuracy on such, say, 3-operand arithmetic calculation tasks. So we wonder like whether those language models solve this problem in the same way as humans. But also note that it's interesting to see that for some reasons, for this Llama 8 billion model, it can solve other kind of operation combinations, but it somehow gives like a super low accuracy on this A minus B plus C problem. So we think that might be something is going wrong inside the language model so that it does not have a very clear way to address this problem. So again, let me just show the key takeaway. So we see that language models do not follow the same compositional way as humans in solving this arithmetic expression. And what happens instead is that, first of all, we see that those language models will wait for almost half of the layers. And by waiting, they basically calculate only very generic representations about the context in this input expression, but it's not doing anything specifically about the operation. So after these long waits, it suddenly started to transfer the information about the operand and the operators to the last token position. And then it completes both operations all together in the last token position in like representation calculation. So this is very, very different from how humans do the task, and we do not really observe any compositional sense inside the language model. And we term such a subgraph as AF1 or all for one, because we see that the model basically aggregates all of the informations only to the last token position, and it rely on the single position to complete all kinds of calculation. So I will skip some details, but basically we introduce like two approaches to ablate some of the representations in the language model, so that we can understand how much weight can the language model do in the early layers, and how does it actually transfer the information from different positions to the last token position. And we do see that, say, for the Llama 3 8 billion model on the A plus B plus C, this kind of arithmetic calculation task, you can the language model can wait up to like 15 layers. So this is very surprising. That means even the language model basically does nothing in the first 15 layers. It can still like succeed in solving this arithmetic expression. And we also see that after these long waits, the model does need like at least 2 layers to transfer the information from about the operand and operators to the last token position, and this transfer is necessary. And then all the remaining calculations is executed by the last token only. And we do see that such a very simple subgraph can give us like a very high faithfulness score as shown here, although the faithfulness score for this A minus B plus C task is very low because the model itself does not perform very well on this task. So we think that the model does not have a clear internal mechanism to do these tasks, and there's no way how we can extract any pattern from that. And we also have the results by like changing different like combinations of, say, how many layers we can wait and how many layers we need to transfer the information. And the key takeaway here is that for the Llama 3 model, layer 15 and 16 are the most important layers for the information transfer. So you can skip other layers, but these 2 layers must be included for the information transfer. And in fact, those layers they have like their attention heads play an important role, but what happens is that like most of the attention heads are not important, and only very few attention heads will have a strong impact on how those information should be transferred to the last token position. And when we try to visualize the attention pattern of those heads, we clearly see that those heads basically attend to different operands in the input expression. So that explains like how they actually function internally. We also have more results when we try to understand the faithfulness of this AF1 subgraph, but under some language variation. For example, instead of directly saying like A plus B, we can say the sum of A and B is, or we can make it like in a question answering format, like what is the sum of A and B answer, right? Or you could also make it like a more complicated math word problem or the Python program, but all of them are corresponding to getting the result of A plus B. So we see that the very like simplified AF1 subgraph can actually generalize with a pretty high faithfulness to several different language variation or the format variations. But still, there are this math word problem and the Python program where this AF1 subgraph does not show a high faithfulness score. So we think that it might be because the math word format or the Python format will actually need the language model to develop other mechanisms to first abstract the A plus B problem before it it does a calculation to solve the problem. And those mechanisms cannot be covered by the AF1, which explains this low face release score. Cool. So yeah, so sorry for describing this part in a very short time. But basically we see that when language models succeed in this like simple 3-operand arithmetic calculation task, they do not really follow the same compositional way as how humans solve that. And that might explain some observations we empirically find out. For example, if you ask the model to do a calculation with some real numbers, say extremely large or extremely small numbers, it does not do well. And if you have like more operations than just 2, then the model could also fail very easily. So we think that it's likely because the model does not compositionally solve the problem. So and as a result, it couldn't generalize beyond. And there are still more things to explore, such as how the mechanisms are complementary mechanisms for abstracting the problems are needed, and how we can connect that to the downstream effects. And in our task setting here, we only consider the direct token generation, direct answer generation. But these days, there are also the wide applications of language models in a long COT chain of thought reasoning formats, which cannot be explained by our subgraph. I'll also skip the remaining slides, but those are basically some other from other work, which also tries to understand how language model or the COT elicit the language model to perform arithmetic reasoning. And for example, here we discovered that there are many like arithmetic neurons developed inside the Llama 2 model. And we see that those neurons, their activation has a really good correlation with their empirical results. And we see that it can be used to explain, say, why sometimes you see like let's think step by step has a better performance than like take a deep breath, right? So there are different ways how you can decide a COT prompt, and they have like corresponding accuracies. And we see that those accuracies are a result from, say, different kinds of like different extent of activation, neuron activations internally developed by the arithmetic neurons. And we also use this neuron activation as a lens to explain a lot of like empirical observations made by prior work. But one thing to note is that the neuron activation is only necessary, but not a sufficient explanation to give like the whole, like a full scope of understanding of how language model reason. Yeah, so that's all of the both project that I want to present today. And also like very quickly, I want to say that interoperability is something really helpful, but we need to, meanwhile, there are also a lot of critiques about interoperability. Say people wonder like why should we do interpretation, right? It's a very time consuming work, and is it worth doing that? So we really call for actionable interpretabilities so that we can discover useful insight for downstream applications. And we should also do that in a systematic way in terms of generalizing the insight from a single language model or a single task to a family of language models and a category of tasks. And finally, my group also work on some human-centered explanation work where we try to see how we can turn a scientific interpretation into human understandable explanation to actually help the end users of language models. Yeah, so my organization may be new to many people in the talk today, but we are actually very close to Washington, D.C. And if you are nearby, you're welcome to visit us. And thank you, and sorry for like running over time.
Well, thank you very much for this very nice talk, and no worries at all about the time, no problem. So now it's time for questions from the audience. So as usual, feel free to write your name in the chat and I'll give you the turn to speak. So we have two questions written in the chat. I can read them. The first one is, do you think it will be easy to adapt mechanistic interpretability to other architectures, such as the SSM using Mamba?
Yeah, that's a very good question. I think it's completely possible, and I actually have seen a recent paper in Triple AI this year, which applied Mech interp to understand the Mamba architecture.
Okay. There's another question from Christian Lucas Cudero. He says, I recently came across the preprint, The Illusion of Diminishing Returns, Measuring Long Horizon Execution in LLMs by Xinyan Collaborators 2025. It investigates how models degrade in simple arithmetic tasks due to self-conditioning on their own errors and distinguishes between reasoning and execution. Do you think these findings relate to your analysis of how LMs succeed or fail in arithmetic reasoning?
Yeah, I think this is a very good question. I do believe that actually as I show in the let me see. Where is it? In the end. So for example, for math word problem, so I'm not sure like what particular like arithmetic task setting this paper is studying, but as we shown here, even for the straightforward like math word problem, it seems that the language model does need to ablate the problem abstraction parts from the arithmetic calculation, the execution parts. And in our work, we mainly focus on the like very straightforward like A plus B plus C, this kind of setting, which tries to get rid of this problem. So I think yeah, I think in the AF1 subgraph, it might has integrated both the reasoning and the execution parts. And to be honest, I think this part is not so clearly like discovered when we are trying to understand the F1 subgraph. We see that like after information is all transferred to the last token position, the model will just complete all of the calculation there. But when we use the logic lens to understand how it actually does the computation, we still couldn't find any say intermediate results from the last token position. So it's not super clear like how exactly it does the execution, but very likely it simply just like immediately come up with the final answer of these like two operations. I hope I answered the question. I'm very happy to read this paper offline and get back to you.
Yeah, so Christian says, thank you for the answer. So I guess he's happy with the answer.
Thank you. It's a really good question.
And now, well, Guillermo Gomez, go ahead.
Well, first of all, thank you very much for your talk. It was really interesting and a really beautiful insight into the LLM's working. I have a few questions. I'll try to be brief to go over the time. First of all, how do you, because this was unclear for me, how do you translate component activation to accuracy? Because you have this rule, and it's not that clear for me because I guess there are interactions as we go further into later components. They are influenced by the early ones. So I don't know how do you map exactly.
Yeah, so I think you're referring to this result, right? The task accuracy.
Mm-hmm.
Yeah, yeah, I should have added a formula here, but actually the thing what we do is very similar to logic lens. So basically you can imagine that say for every attention head, it has an intermediate representation writing into the residual stream, and same for the feed-forward neurons. And what we do is to project this representation directly to the vocabulary space with this logic lens approach. Like we basically multiply that with the unembedded matrix. So unembedded matrix is typically applied in the output layer for predicting the next token. But here we just apply this unembedded matrix two intermediates, attention head or neuron representation, so that we can see whether this representation has already been able to promote or rank the correct answer token on top. And from that, we can calculate the task accuracy.
Okay. Well, do you have any? I've seen many GitHubs as you talk of different work you have. Can you guide me or recommend some GitHub when you have this implementation, and I can take advantage of some framework for that?
Yes, absolutely. So I think for the NeurIPS paper, we are still organizing the code, but we'll release the code very soon, definitely before the conference. And for the EMLP paper, I think we should already have a link to our source code. So yeah, feel free to play with it.
Okay, I will definitely.
Yeah.
Just one final question. In the cases of success and failures, especially on success, where the parentheses or the task is predicted correctly, is it because of a really strong component activation, or is it because of the collaboration or the agreement of different components innovating themselves and activating themselves when corresponding?
Yeah, that's a very good question. So when we are trying to understand like how language models succeed in this arithmetic calculation task, we do not really look into the internal mechanism, but I think that's something we can do next. Like here, we only try to find simplify the subgraph to understand the information flow, but it's also possible that, for example, some of the attention heads or the feed-forward neurons, they may have implemented like very different mechanisms to contribute to the task. Oh, and actually one paper I'd like to recommend. Let me see if I can. Okay. So there's a paper called, I don't know, can you see my browser?
Yeah.
Okay, cool. So this is a paper I find to be very interesting. So it's also on arithmetic reasoning task, following like very similar setting. And what people find there is that the model indeed have to use like a bag of heuristics, not necessarily like different circuits, but it's like it has different heuristics. Say what's the result if you have like two operators, two operands, minus here, but this two operand has a certain value range, then will be the range of the result. So the model internally relies on a lot of such heuristics in order to do like even very straightforward like 226 minus 68 task. So
Okay,
yeah,
thank you
I
very much
highly
for
recommend this one. Yeah.
Yeah, I'll go thoroughly through it. Okay, again, thank you very much for your time and your talk.
Thank you.
Okay, any other question from the audience? Because otherwise, I think we can end this seminar here. Last chance. Any other question? No? Okay, so I want to thank you, Professor Yao, again for accepting our invitation and for giving this extremely interesting talk.
Thank
and
you.
also, of course, thanks to all the attendees for the questions and comments. Thank you very much.
Everyone. Yeah. If you have further questions, feel free to email me.
Thank you again.
Great.
Thank you.
See you.
Bye-bye.
Bye-bye.
Bye-bye.